So for today's meeting, we'll go over a few logistics similar to last time for those that were able to join us before. All of your lines are muted for today's call. We're going to have several question and answer breaks throughout today's webinar. At any time, you can type in your question using the question box that's available on your webinar toolbar there. If it's technical related, we may respond right away with a written answer, or we'll wait for a break and then we'll discuss it. But feel free at any time that you think of a question, go ahead and type it in there. Only we see those questions. If it's something that we want to share with everybody, we can send the question out and the answer to everyone. But for the most part, we'll review those when we have our breaks. Also, if you have any technical issues throughout the webinar, go ahead and throw a comment in there and we'll be able to see that and see if we need to make some changes with our broadcast. We do record these webinars and we'll post them to our website. Last week's was recorded well and has been posted. You can watch that if you didn't have a chance to attend. And then also in your webinar tools, you'll see a section on handouts. There are 5 PDFs uploaded there for you. One includes kind of a handout, I guess I'd call it, with specific links that we'll discuss throughout today's webinar. So useful follow-up tools or resources that you can explore. Oops. And then I went ahead and kept some of the previous handouts that we used last week, as far as we won't really be discussing permitting or applying for permits, but those are also available. So if you have questions about when you need a permit for dam construction or what kind of things you need to submit for permit application, those documents are available again. And our dam maintenance manual that goes through a lot of the best practices for taking care of your dams is available. And then there's also a copy of today's slides if you want to be able to go back and look at the specific things. This is our second in our 4 webinar series for the month of May. Today we'll be talking about how dams fail and proper dam maintenance. Last week was our kind of our 101, and like I said, that's recorded and available. And then next week we'll be talking about finding and hiring engineers. And then our last week we'll be talking very technical oriented on engineering design and what's needed for permitting, and then potential changes to our dam safety rules coming up.
Hey, John.
So on to, yeah.
I'm going to interrupt. I think you're not sharing your screen yet.
Okay, you're not seeing it because it.
I don't see it. It says it's for view.
If anybody else sees it, I think, let's see, Adam typed in. Looks like, I wonder if it's on your end, because I think.
Does it? Yeah.
Yeah, we're getting feedback that people are able to see it,
because I don't see feedback either.
Huh. Yeah, I wonder if you'll have to refresh or rejoin or something, but.
Okay, I'm gonna jump out and come back.
Okay.
Yeah, because I don't see any questions either.
Okay, yeah, yours must have locked up on you. Well, so you know, that's a good way to introduce Casey, I guess. So as I said, I'm John Garton, and that's Casey that'll be helping out, and he's specifically going to be keeping an eye on things like he's doing. And hopefully it does start working, and he'll be keeping an eye on your questions as they come in as I'm going through the slides. So and that's our contact information as well. So anytime you have questions, you can call or email us. Right now, us being out of the office, usually email is a quicker way to get a hold of us.
Excellent.
So for today's webinar, we'll go through real quick a little bit of Dams 101 for those that weren't able to attend last week, just some of the basics. And then we'll be talking about the primary causes of dam failures. And we'll go through several case studies, really over the last 10 years, some significant failures, a few in Iowa and a couple national. And then we'll be going into proper operation and maintenance, which involves, inspecting your dam, keeping an eye on it. And then, so for kind of a recap of our Dams 101, as we talked about last week, the two basic things that dams have to do is safely hold water and safely pass extra water without compromising, usually overtopping. So we'll talk more about these, but obviously what causes failures is when one of these two things doesn't work well. Last week we went over, parts of a dam, which will come into play a little bit today when we talk about failure mechanisms. So as you recall, we have our reservoir upstream of the dam, our principal spillway, inlet riser, upstream slope, crest of the dam is the top. The groin is kind of where the dam meets the abutment. Outlet works is where our water comes out. A lot of our dams have internal drains and filters, and those drains will have outfalls, separate pipes usually that can drain those internal filters. And then most dams have an auxiliary or emergency spillway to carry extreme flows. Looking at the inside of a dam, and this drawing kind of shows a cross section. So as we mentioned, embankment dams are typically made up of a clay core that's as water impenetrable as we can make it. And then if we don't have enough good clays, we zone dams using our best materials in the middle, and then upstream and downstream materials to help support that clay core. And most of the time in Iowa, we do have enough clay available nearby that we build a homogeneous dam. We build one clay dam with a topsoil cover. And then we typically, a lot of our larger or higher hazard dams, we include filters, which help intercept any kind of seepage through the dam and safely drain that out. It's tricky switch. So how do dams fail? Probably one of the most common ways that we see dams failing is that they overtop. Earth embankment dams are really good at holding water, but if we get erosion down the back side of a dam, that steep back slope really lends itself to fast velocities if we get water flowing down it, and that can erode the materials, which obviously takes the support away from the dam. Spillway scour can also be an issue. And then another very common way is internal erosion along conduits, piping from rodent burrows, actual structural failure. So if a pipe collapses or a chute or something, concrete or metal just gives way. We can get contributing to some of those dam failure causes can be uprooting of trees or vegetation, long-term erosion, doing damage to the dam itself. And same thing on the upstream side, if we have continued wave erosion that's eroding the upstream face. And this is really a rare risk factor in Iowa, but liquefaction is often caused by earthquakes, which basically, once the ground shakes, soils can become liquid and collapse. So why do we care about dam failures? Obviously, dam failures can cause loss of life, downstream property damages, environmental impacts. You lose the reservoir itself, and of course, you have costs associated with with replacing the dam and everything downstream that was damaged. A few photos of some historic failures. Obviously, floods in general cause significant impacts, and dam failures cause these extreme floods. And then, of course, like we said, even if you don't have downstream failures, you're losing your reservoir, which is the whole point of your dam. If we look at some of the common causes of failures on this graphic here, oftentimes we get excessive trees and brush on the dam, which can hide rodents, can hide seepage, can contribute to erosion, those sorts of things. Dams can have cracks in them. Cracks are usually caused by differential settlement of the abutment or fill. As we talked, dams can overtop, can have cracks that run transverse or longitudinal to the dam. Sinkholes, foundation stability, and we'll go over these in more detail. So as I talked about, one of the most common causes of failure of a dam is just overtopping. So this can be caused by either a clogged spillway, meaning that we can't get the water out the way it's supposed to, or even if the spillways are operating at full capacity, it just might not be enough for that rainfall event. Our low hazard dams around the state, as you'll recall in our last webinar, which is about 90% of our dams, really were only designed for about a 50-year flood. So when we get 100-year floods or some of our more extreme flood events around the state, which we certainly seem to get a lot of, those dams frequently will overtop, and that'll cause erosion of the backside, and sometimes they breach. Yeah, as we talked about, that can erode the embankment away if we have enough flow. Just some pictures of that going on. Really, once you get head cut started, that's when things can rapidly progress through. I'm going to play this animation here. The way we have this GoToWebinar set up, I don't think it does the best video transmission for you guys. So in my handout, there are links to the, I'm going to play a couple of these animations. So if it seems a little jumpy for you, you can watch these afterwards through YouTube. But basically this one just sort of reiterates kind of the obvious that when we have a dam that receives a lot of rainfall upstream, that reservoir is going to fill up. And like we talked about last time, that's kind of by design. We do design dams to store that extra water, but sometimes we don't have enough storage or enough spillway capacity, even when we use our auxiliary spillway, which is happening here. So basically the dam keeps filling up. We get that overtopping. You can see in the middle there, we kind of got a major head cut started. And really, once you get that opening between the downstream and the upstream reservoir, it's really going to progress quite quickly. So like I said, if that was a little jumpy, you can watch that later. Another very significant cause of failures is, and this can even occur when we have water at normal level, is seepage through the dam that then carries materials with it. We call that piping or an internal erosion. So essentially that's when we do have an area of the dam that is allowing seepage, and the seepage starts to get to a point where it's transporting material, which means we're basically making that conduit, wherever that seepage is coming through, if we start to move material, we're going to make that path even bigger. So a bigger path means more water flowing, which means more materials being transported to the point when we have a full tunnel between the downstream and the reservoir, and then it rapidly enlarges and fails the dam. And that really can happen anywhere. You know, water is always trying to find a weak point. That can be due to poor compaction. It can be due to poor foundation conditions, you know, bad cutoff of the foundation. And also anytime we put our spillway conduits or other utilities through a dam, that allows potentially weak areas that water can flow along. I touched on a little bit on the last slide where we can also get differential settlement of a dam, which can open up a crack in the embankment. Picture of an example, a few years ago, we had a large dam open up a new seepage path. And kind of the inset picture there just shows we were trying to monitor that seepage and see if it was growing. So the owner kind of funneled it through that pipe and sort of like a furnace vent there, so that we could put a bucket under it and measure it, see how quickly that was flowing. But significant amount of seepage coming through that dam, and luckily we were able to draw it down and later repair it. So that didn't lead to a failure, but definitely an example of a large seepage path. And I went ahead and did put some graphics in here, since the animation I'll show, like I said, I'm not sure how well those play through. So this sort of demonstrates what we've been talking about. So basically seepage can find a path, and it can start out as a very small trickle. And a lot of dams do have seepage that is contained, but anytime you see seepage and you start to see any kind of materials or muddy water or cloudy water coming out, that means that material is being transported. And as that material is transported, you know, the pipe can get larger, transporting more material, leading to, then you would start to notice sinkholes upstream, and of course large voids showing up. This one obviously is after the fact when it's mostly drained. Similarly, so that kind of showed just a seepage above a pipe. One of our largest concerns, and one thing we pay special attention to when we look at dam construction designs, is the treatment of anytime we put round conduits in a dam, it can be difficult to compact under that pipe. That's kind of a weak area by nature. So different design methods we have to help deal with that, depending on the size of the dam and hazard class. But that can be a weak area where we can get that piping and internal erosion going. So kind of an example of that is here. This is really, this started with water coming out of the pipe, a deteriorated pipe, but this just shows that water flowing along a pipe can pretty quickly carry that soil away. And we'll try to play this animation. So those of dam owners on the call, you know, like I said, seepage is pretty common, and that's one thing you want to do, is not take it for granted. You always want to keep an eye on it and note any changes and see if there can be any improvements made to better filter that, and just let it be. So here it just kind of shows the animation of that tunnel. Basically, we can just see that the more water we get going, the more material erodes, and it just kind of has a exponential growth in how quickly that can grow and create a full tunnel through the dam, which then could cause a collapse and then major loss of a large portion of the embankment. So another cause is embankment slides. This is when the embankment itself becomes unstable. Usually this is when the dam is saturated. As soils, the more water you have in an embankment, the weaker it is basically. And that can happen. We've seen that both from seepage into the embankment, or sometimes we get surface slides on the downstream slope just because we've had a ton of rainfall leading up to that event. So sometimes we can even just get rainfall infiltrating on the backside and causing some minor slides as well. And of course, you know, if we do get, one of the things we try to point out is when large trees are allowed to continue to grow on dams, they, you know, as they get older, they blow over. You can lose a significant amount of material when they do that, weakening the embankment. A little sketch of a typical embankment slide here. Typically, you'll know it's a significant slide if you see this scarp up top. You'll usually see a vertical or near vertical opening, and then you'll see usually a bump out below it that kind of indicates that you have a major slide. So kind of an example here, surface slide, we see the material kind of accumulating here. Obviously, you can see the major drop here. A little bit more of a minor, just that vertical drop. We've lost that part of that embankment. Kind of the other main cause of failure of dams is structural failure. Spillways themselves can deteriorate. We can have pipes that rust through. We can have concrete cracking and deterioration. We can lose walls or floors. And then another common one is actually having, when we have concrete spillway chutes, we can get water starting to go underneath the chute, which can erode the materials underneath that concrete chute. And that's kind of particularly dangerous because we can't see that happening. A lot of times you can get significant voids underneath our concrete chutes before they're ever discovered. And then of course, if we have when we have concrete dams, any kind of instability of the concrete itself, cracking or mass movement can occur. Here's an example of that spillway pipe just hitting its max age and has rusted through. So corrugated metal pipes definitely have a limited age of 35 to 50 years and will need to be replaced. Here's an example of a poorly maintained concrete chute. We've got, you know, open cracks so large that we can get large vegetation growing. We have vegetation growing around the walls and you know, water getting into the cracks and whatnot. Another example of a older chute. This one since has been replaced. All right, so about a half an hour in. This is kind of our first break. We're going to go on to some specific case studies of dam failures, but wasn't sure if there was any specific questions on some of the dam failure mechanisms.
I don't see that we've gotten any questions.
Okay. So if you think of something, go ahead and, like I said, at any time you can type that in, and even if it's on what we've talked about before now, go ahead and type that in, and we'll talk about it in a future break. So our first case study I want to talk about is Lake Delhi. I'm sure a lot of you have heard of this lake up in northeast Iowa. This one is kind of especially relevant. I started at the DNR and the dam safety program about 6 months before this one failed, so it was certainly a learning experience, my part and Casey's part as well. I think Casey hadn't quite started yet when it failed, but he did shortly after, so we've watched this one closely. Picture of the dam, historic picture of the dam. It's located in Delhi, just southeast of Manchester, Iowa, Delaware County. It's an older dam, built in 1927. It was a hydroelectric dam. It held 3,790 acre-feet of water. If it filled up the top, we had about almost 10,000 acre-feet. 58 feet high from the downstream toe. Created a very large and long impoundment. Basically, it dammed up the Maquoketa River. So we had a 9-mile long impoundment upstream of the dam. Wasn't very wide per se, but a lot of homes and development had happened over the years that used that impoundment. 1973, they no longer maintained the hydroelectric generation, wasn't profitable anymore. And it was turned over to the Lake Delhi Recreation Association that, like I said, the homes that surrounded the lake. And it did have inspections every 5 years, both by the DNR and they were required to hire a professional engineer, engineering company to do an independent full investigation as well. Our last inspection report on it had noted some things. There was some upstream erosion. The gates were really, all the gates were in pretty bad deterioration. One of them was especially bad, but they were at the time working on repairs. They did have new gates ready to put in, and they were getting ready to do a lot of work on the dam. But they did have a lot of trees and brush that we'll look at in a minute here too on the downstream side. So here you can look at, this was a picture of the gates, the old powerhouse, the hydro was in here, and this is that earthen embankment that had a huge amount of trees and brush. This is the upstream face. Like we said, there's a little bit of, not too bad, but a little bit of erosion that was noted. The spillway gates are down at the far end. So this part was the earthen embankment, kind of a combination dam, earthen embankment and concrete. Another picture, there was a road over the dam originally. Once again, you can see that really pretty heavily wooded, so it's it's hard to inspect and see if there's anything going on, which we'll talk about in a bit. Like we said, they had some issues with the concrete and the gates. This is leakage around the gate, more leakage. This is after the failure, but you can see some of the historic damage to the concrete here. Like I said, they were planning to do repairs, but hadn't gotten to it yet. So in 2010, we had really record rainfalls upstream of the dam. Starting on Thursday night, the 23rd, they started, the way it kind of worked was they could pass low flows through the old hydro gates, but then as they got larger rainfall events, they would slowly open up these 3 gates. So that's what they were doing. So they, like I said, they opened them all up, but one of them kind of sticks, and so one of them could only be opened up to about 6 feet compared to, I think, 15, 16 feet they should have been able to open up. So they were already kind of in flood fighting mode when they got a weather service forecast that says, hey, we're going to get between 11 and 14 inches over over the next 2 days. So they knew some tough times were coming. They were keeping a close eye on the dam. 3 a.m. Saturday, they noticed a whirlpool and some roadway settlement on the south end of the dam, which is that earth embankment. 5:30, as the sun started coming up, they noticed a significant sinkhole on the upstream slope, which is indicative, as we talked about before, that we've got some kind of piping, something going on inside the dam if we're seeing a sinkhole that large. And then, like I said, as it got more light, they could see that there was water coming out the downstream of that embankment. Because of those significant observations, they basically got everybody off the dam. You know, it wasn't safe to try to mitigate anything at that point. Water level during this time continued to rise. They kept getting that peak flow coming in. 10:30 a.m. the dam actually started to overtop, and by Saturday afternoon the dam was fully breached and emptying. We'll show some pictures of that. This is just kind of a, this is the, let's see, Lake Delhi Dam is down here. This is this outline is part of the watershed of the Maquoketa River, and these are the rainfall amounts received in that area. So anywhere from 8 to 12 inches in the upper part of the watershed. Showing, this is a kind of a cross section of the river. So we're to the left here, we're at the downstream, and we're just looking the river profile as we go upstream, up to Manchester. And then the lines at the top here are the different flood levels that occurred on the Maquoketa River. So the lower two lines are green and red. Here, these were the previous historic flood levels of the Maquoketa River. In 2010, this black line at the top was the new profile that was measured. So historic flood, little zoom in on this was the traditional lake. Really, the lake in the previous past floods really hadn't seen a significant rise. It didn't, the spillway was able to keep up, really didn't have a significant flood or increased flood depth on the dam for those previous flood events. Pretty minor. Versus 2010, we had significant additional height on the dam. So kind of a new test situation. Obviously that caused flooding even without the dam impacts. This is upstream in Manchester. You see flooding through the town. Here at the dam, you can see the water coming up, starting to flood a lot of these boat lifts and homes. Haven't quite started over top yet. And then this kind of shows the progression. So as we started to get overtopping here, we start to see, you know, we're losing that embankment. Here it's continuing to erode, breaching through. And then this is looking downstream where previously we saw all those trees and brush. There's looks like a boat going over. I think that might have been the barge that they were using to work on the dam, starting to go over. Yeah, it's that work barge. And then, yeah, the road, the dam's, the embankment's completely gone. And then this was what was left. Guardrail held up quite well, though. Some of the after pictures, some of the, what's kind of amazing is just some of these boats that got pulled through the gates or even trapped on the gate piers here and twisted. One thing to note that we'll talk about in a minute is the earthen part of the dam did have this rock or concrete wall to help stabilize the dam. So that we can see parts of that concrete wall that was supposed to hold the water here that eventually broke away. Here you can see the other part of it. And it had a sheet pile cutoff along the foundation. close-up of that reinforced concrete wall. And then left with an empty impoundment. So one thing interesting about Lake Delhi Dam is nationally it got a lot of interest, and there was a push that said, hey, you know, really we have to, when dams fail, we really need to do a better job of investigating them, to put together reports so we can learn from them and see what happens. So that happened in Iowa in 2010 for Lake Delhi. We were able to put together a dam failure investigation. FEMA helped out. The National Dam Safety Program, National Dam Safety Review Board, helped put together a team of 3 federal dam experts, one from the Bureau of Reclamation, one from the Federal Energy Regulatory Commission, and one from the Army Corps of Engineers. And they came and inspected the dam and interviewed everybody that had anything to do with the dam over the history, and they put together a report. So that was really useful to have a true forensic study of you know, what exactly happened and what led to the dam, and then some other what ifs, you know, that had happened. You know, what if they had opened the gates, or what if different scenarios, so that, you know, a lot of people start putting opinions out when things like this happen. So it was nice to have a report that was able to look at all those theories in detail. But really, the key player in this was this concrete wall in the earth embankment. You can see here on kind of the upstream end of the embankment. But one of the couple flaws with it was that it was 6 feet below the top of dam. So when we had that new record level in the impoundment, we basically had water level that was above that concrete wall. We also likely didn't have very good compaction up against the wall behind the wall. So once we got water above the wall, seepage was likely rapidly occurring. And this is some of the forensics they did as well, and just determined that even if the dam hadn't failed, it would have had significant amount of time of flow over the top of the wall. But there was about 17 hours. And so we can just see that once that water level got high, and we started seeing these whirlpools, and we started seeing exit discharge. And so water was pretty much just flowing right through the dam even before it overtopped. Some of these pictures show that, you know, we had that real cloudy discharge even before we had overtopping. Here and here. And so, like I kind of hinted at, the cause was basically that internal erosion, or what we called piping. Once the water level got above that wall, there really wasn't anything to prevent. It was real sandy soils, and that's why they put the wall there. But since it didn't go to the top of the dam, it was kind of an inherent weakness of the dam that was finally exploited when we had that record flood. So this was kind of the first national forum dam failure investigation. So it really spearheaded some committees on the national level, developing guidelines on how best to do these. And some takeaways for owners is that, you know, anytime your dam is seeing new record levels, be very alert. You know, you're now fully testing your dam where maybe it hasn't been before. The trees and brush on the dam, you know, they might have seen some problems a little earlier had they been able to see down the back slope of the dam. And then a big takeaway is, you know, we inspect the dams every 5 years, but, you know, was there ever, since it was built in 1927, was there how many really fully thorough engineering reports completed that looked at it from a fresh perspective and said, if we design this dam today, what would we do different? And are there weaknesses between what we would do now and what was done in 1927? So we need to design reviews occasionally on these larger dams. And it was, as most of you know, was rebuilt and completed in 2016. Basically where that breach occurred has now been put in a large labyrinth weir spillway that can handle over double the flows that happened in 2010. So that dam has been refilled and restored.
Hey, John.
Yeah.
Before we move on to the next one, we had a question about
Okay.
Delhi. You had a slide that showed the flood profile with some historic numbers. And the question is, the 2010 peak flow wasn't much higher than the 2004 peak flow. Why was the rise in lake level so much more?
Yeah, good question. I haven't dove into Delhi in a few years. I mean, one thing that did contribute obviously was the third gate didn't open fully, so that they were able to pass less flow than in the past. And then like we talked about last week with the bathtub, if we hit that capacity, the reservoir will continue to rise. So it might have been a little bit higher. I think there was also, as I recall now, this flood tended to have a lot more volume of flow versus, even though the peak flow rate was similar to maybe 04 or 02, we just had a lot more volume coming in too. So we had a higher flow of water for a longer period of time. So the lake really wasn't able to store as much peak flow as it could have for the previous floods. That's kind of what I recall. Is there anything else?
That was it on Delhi.
Okay. And that report is available. I believe we still have that linked on our website. I'm not 100% on that. I can't remember if we took that down finally or not. But if you're curious on more of that, that full report is publicly available. A more recent national dam incident that you might have heard of is the Oroville Dam. This actually, now we're going to the largest dam, the tallest dam in the United States, 770 feet. This is part of the California Water Project. It's owned by the California DWR. It's water supply primarily, and then generates hydro and provides flood control. 3,900 square miles of drainage area, and a lot of that is snow, collecting snow melt from the mountains, so they can use it throughout the year. Located just north of Sacramento. The dam consists of a very large earth embankment, and this is a zoned embankment. But primarily the issue was with the service spillway, they call it, and that actually was constructed on the abutment of the dam. So the dam itself, really this wasn't a dam failure per se. The dam really doesn't have any significant issues or had any significant issues in 2017. It was an issue with this service spillway. And I'll also point out from this picture, the lake's emergency spillway or auxiliary spillway was over here. It was a large weir, about 30 foot tall in this section here, and then kind of got shallower and shallower, but actually extends way through this parking lot. This is kind of a boat ramp type parking lot, but this entire area, this entire length serves as an overflow spillway that when activated would just flow down this this rocky kind of abutment. So, and these numbers are going to be really large for what we're used to in Iowa. But in February of 2017, they were releasing 50,000 cubic feet per second, which is a pretty routine amount of water. The spillway could handle about 250,000 CFS, or designed for 250. So a lot of water, but well within the design of the spillway. But at that flow, 50 or 55,000, it actually started to break up. They need to, that's the only way, the primary way they get water out of that impoundment, and they were expecting more, so they had to keep water flowing. But they were minimizing, so they were trying to hold it down to 50,000. They didn't want to make it worse, and we'll see pictures of all this. And so by February 10th, because the lake kept rising, they were going to use the auxiliary spillway for the first time ever, which occurred on Saturday. And then on Sunday, they actually had to order evacuations, which we'll talk about. And then they turned out flowing water over the service spillway was worse than using the, I guess, using the auxiliary spillway was causing worse damage potentially than upping the flow through that damaged principal spillway. So here's some pictures of the initial damage that occurred when that started breaking up. So this was really this area of damage, and this is about a 200-foot wide spillway. This was after they noticed it, and they stopped the water temporarily just to be able to quickly see what's going on there. And this we talked about. The reason they were doing evacuations is because as water started to flow over the auxiliary spillway, they were getting erosion of that downstream abutment, and they were getting some head cuts that were going close to that wall, and they were worried if that undercuts that wall and that entire 30-foot high wall with a huge lake behind it collapses, that's going to be a very massive flood wave downstream. So since they were getting out of the erosion, they basically had to increase the flows over the service spillway, even though it was damaged. So here you can just see that 100,000 CFS. For those in that understand, that know Coralville or Saylorville, their peak flows are around 20,000 when they fully open their spillway gates. So we have about 5 times what comes out of Saylorville when it's fully open. And of course, then that just caused additional damage of that eroded area. And then they were just really crossing their fingers that it didn't continue to climb up toward the gates. Here you can see the water leaving. Really, it had this kind of flatter area, and then it really got about, I think, 25% slope or something on the downstream. So it really cruised down that backside. To give you perspective, this is the height of those gates. It's a truck, and so this is the very large spillway. And the auxiliary spillway, and it really wasn't a lot of water over the emergency spillway. It was about, well, they max out about 2 foot depth, I believe. And even 2 foot of depth over such a long length was kind of converging and causing significant channel erosion downstream. Here you can kind of see, so it flowed over kind of uniformly, but then would find, very channelized areas, and so it would start to cut and started to erode up toward the dam. And no one was 100% sure, and you only had hours to make decisions. Would it have held? Probably, but are you going to tell people downstream that we're probably sure that this wall will hold as we get erosion up toward it? So the emergency management officials were like, well, we have to evacuate if we're not 100% sure that this thing is gonna hold. Some more of that downstream erosion from the auxiliary spillway. And see, we can just see that it just kind of funneled down. And a lot of the historic reports, considered this whole abutment area to be rock. It's a very rocky area, but you know, a lot of the design assumptions that went into both the service spillway and the auxiliary spillway is that, well, it's all built on rock, it's all rock downstream. If we get these large flows, it's just flowing over rock, it'll be stable. But really, it wasn't like solid rock. It was very rocky soils in various depths to true solid rock. So you can see that it actually was a lot more highly erodible than they assumed in some of the early designs and construction. So then, you know, you can just see some of the scale of the damage and scale of the spillway here. So like I said, really Delhi kicked off setting the standard for dam failure investigations and making sure that these are done. So obviously this is on a much larger scale, but a team was stood up and looked at, you know, how did we, one of the largest dams in the country, how did this happen with such a routine flow, and how did we miss it? How do we miss what would cause this? Through all the inspections, through all the reports, through all the oversight of this dam, if it can happen to this dam, then how do we know any dam is safe? So what they found was, and I won't get into too much of the technical details for this webinar, but basically water was getting underneath the slab. And with that much flow and that much velocity, it doesn't take much. If you get a little bit of that slab lifting up, that water comes down that chute so fast that it can pull a section of that slab up. And once that occurred, it really could really quickly erode that underlying weathered rock that, like I said, when they built it, the people on site just kind of built it as though they were building it on solid rock, and it really wasn't. It was really weathered bedrock and a lot more erodible than they had assumed. We'll talk about one of the most contributing. So really one of the biggest contributing factors of how that happened was that, you know, there was really a disconnect back in the 60s and 70s between designers, engineering design of dams, and then it got kind of handed off to the field. So you had an owner's engineer representative out in the field, and you had the contractor, and so they would take the plans, and if they noticed anything different in the field or had issues or questions, they would make the decisions out in the field, and they wouldn't always talk back to the original designers. And so there were some changes, so some significant changes in the design of the chute that reduced the thickness in some areas from what was supposed to be 15 inches thick to only 7 inches, and I'll show you those. And then, you know, they had said in the design, they said, hey, anywhere you have loose fill or you don't have solid rock, you should over excavate that and fill it with concrete. Well, that would have added a lot of cost because there's a lot more weathered rock and soil-like materials than they had accounted for. So now you're looking at delays and cost overruns. So it was easier to say, oh, that foundation will be fine. So this picture is especially relevant because, and we'll see why in the next picture, but these are where the drains were. So most concrete chutes will have drains underneath the slab because we don't want water pressure under the slab. And we also don't want water carrying materials out from under the slab. So we put drains underneath concrete chutes to catch any water that does leak in. However, because of the way these drains were built, it basically cracked above each drain. And here we'll see, this is the slab here. And it was designed at 15 inches thick. However, they didn't really want to put the drains, you know, into the solid rock where they had it under the slab. It was a lot easier to lay the drain on the surface and then just pour the concrete over it. You know, someone thinking, hey, 8 inches of concrete, reinforced concrete, that's still really thick. We don't need the full thickness. everywhere. So kind of another field change decision. So that created a crack there, which could never be fully sealed. So if you notice in some of those pictures, we always had high flows through the drains anytime the spillway flowed. So we had a lot of water going through these drain pipes that really it wasn't designed to carry that much water. And then this is from the report. Shows a picture of one of those drains, and they put a piece of plastic over it and then poured the concrete. You also see we have really large aggregate and stuff, but it would always crack above there. It was just a weak point. So that was kind of, I don't know if I have a slide on lessons learned or not. No. So yeah, lessons learned really were, we can't ever assume that a dam that's been there for 30, 40 years and everything's working fine. Everything will be fine. There can be inherent design flaws that we haven't discovered yet. And the key thing on that was all the water that those drains carried. From day one, people said, man, that's a lot of water, but it's like, well, what are you going to do about it now? So they were never really fixed. The cost was just too much to think about. And so even on one of the most highly inspected dams, it just said, well, they've always done that. It was kind of that lesson learned of we shouldn't always just say, well, it's always done that. It'll be fine. But since that is such a critical part of the water system in California, it had to be rapidly fixed for the next, and basically the way the water cycle kind of works in Northern California is you would have drier parts of the year and then you'd have these wet seasons when we had the large runoff in the winter. And so they had a very short season to basically fix it or temporarily fix it. So they got the hole plugged in the first season and some temporary walls up. And then they came back the next year and re-overlaid that and redid the upper part. And then they also built this huge roller compacted concrete stabilized spillway downstream of the auxiliary. So here you can see them completely replacing the entire chute with proper drains, proper joints and those sorts of things. And we're talking over $1 billion of work on this that had to happen rapidly. So now another recent dam failure in the news was just last spring, the Spencer Dam in Nebraska. This dam is on the Niobrara River, just south of Spencer, Nebraska, not too far from Iowa. And it was a functioning hydroelectric dam. It was also built in 1927, so in Delhi. Had a powerhouse, 400 chute long concrete spillway, and then a long earth embankment. And it failed on March 14th of 2019. And there was a fatality that went along with that failure. As you recall, the winter leading up to spring of 2019 was very cold. So we had very frozen ground, high frost depth, which also led to very thick river ice and snowpack. And then in March of 2019, we had that, what they call the bomb cyclone at the time, a winter storm occurring in March that, because we had warm temperatures, produced heavy rain at that time. And of course, the heavy rain had really nowhere to go except flowing off the watershed. And then also made all that huge thick ice break up on the river and flow rapidly downstream. So everywhere that ice hit, it would cause ice jams along the river. They suspect there was a large ice jam that occurred just upstream of the dam on a bridge, and then that broke through as the bridge gave way, which really just sent a huge amount of ice and floodwaters toward the Spencer Dam. And then there was a single home and occupant downstream of the dam that basically that entire home was just swept completely away. And there was a report on this dam as well I'll talk about, but it wasn't the dam failure alone that caused that home. It would have flooded no matter what, just because of the significance of that flood event. And those will recall, those on the phone will recall as well that caused our was another contributing factor to the huge flood on the Missouri River that occurred around those time and breached a lot of our levee systems along the Missouri River in Iowa. Both that and the Platte River just had huge amounts of flow and caused some record floods. Here's some pictures of that upstream ice. And here's a picture of just one of the pieces. Pretty amazing. So this was the morning after, I believe. There wasn't a lot of pictures or video at the dam. It was in the middle of the night when most of the flows, I think, came down. Very kind of an isolated dam as well. But you can just see that huge amount of water, and it just busted that dam up. So another recent report came out just in April, and that's available. And it was fairly straightforward findings, I guess. They did do some what ifs as well, but I mean, with that much ice coming down to those spillway gates, it just, you know, they got jammed pretty quickly, which led to water just completely going over the top of this dam and then washing out the portions of it you can see down here, and of course down here, and of course the gates, and the pressures on the concrete was too much for the design. So since it was such an extreme flood event, a lot of the damages would have occurred even without the dam failure if the dam hadn't been there. So those are pretty significant incidents, failures. And then we've got just a couple more minor ones that didn't lead to full failures, but I wanted to point out that these are kind of always happening and something we have to keep an eye on and be ready for. We have the Bedford Reservoir, the Bedford Dam down in Bedford, Iowa, southwest Iowa. Previously was their water supply reservoir. They'd switched to, I believe, rural water in the past several years, and so it was no longer used as their water supply. So now it's more of just kind of an amenity, a little park area, dam. But then in October 2018, we had a call basically pointing out that they're got a little problem here with the spillway, and you saw this picture earlier. So you can see the water flowing out. So obviously our first priority of seeing this situation was, how do we get the water down? How do we get this flow stopped through this breach area? Luckily they had an old water supply line that led to the plant that we could at least get some water flowing through that, get that opened up so we could slowly drain the lake to prevent further erosion of this embankment. Cross section of the dam, this would be the upstream side here. The water would be right here normally. And this is the top of the dam, and then this is the pipe through the dam, and then out the toe here. So looking at a cross section, what really saved this dam is where the problems were, that pipe you could see in a previous picture, and I kind of showed a picture of it earlier too, just completely rusted through. So we had water basically flowing below the pipe down through the bottom portion of the dam here. And then it just slowly eroded all that material with it when we got a high rain event. But really there was no piping noted, no signs of any kind of water flowing along the pipe through the main sort of part of the dam here. So water was flowing through the pipe, and this pipe was fairly solid. And then it was getting out here. So that's where we just saw that really extreme erosion here, and it's a fairly shallow pipe, so it was going to take time to erode down. So if this pipe had been straight through the dam with problems, we would have had probably a much more significant loss of embankment. And if that pipe had eroded through here, we probably would have had piping all the way through, which would have led to potentially a full breach. And this, I think I showed earlier, but just that extreme, if I recall, this pipe was about 50 years old. So just finally rusted through. And that has since been fully replaced. Just completed that last fall, I believe, this spring. Another incident that popped up just last May. A year ago, I get a call from, actually it was observed by, this is John Deere Finance. Oops, I'm pointing at the wrong thing, sorry. This downstream here is a parking ramp. This is in Johnston. This is John Deere Financial Services. So anyway, you had employees coming out here. This parking ramp kind of sits above, about the same height as the dam, or a little higher even, so you could see out. So someone noted that worked there that there's a hole in the dam. So they called us. We got out there right away. And here you can see that hole. So, the homeowners and things upstream, and they don't, this is kind of a native grass mix, so it's not something that's normally mowed. And so it was actually observed by those people downstream and not the owners originally. Closer look, and then when you walk up to it, we had a huge, this is probably a 12, 15 foot deep hole, sinkhole over the dam, right over the conduit here. So another case of these old, you can see in the picture here, it's a corrugated metal pipe. It's the metal pipe. Corrugated metal pipe, they get their strength by those corrugations, those waves. So that means they can make the pipe a little bit thinner. The actual wall thickness isn't very thick. So they do have a limited lifespan. Like I said, probably 35 to 50 years. So this one had basically hit its life, and really just, you can kind of see it just caved in at some point. And once that, obviously once we had a large hole in the top of our pipe, that soil was able to just slowly wash right into it. So luckily this was a very isolated incident with that spillway pipe. But had we had further high flows or a flood event that occurred after that happened, we could have had some major issues, but fairly isolated. So that was able to be detected, and then full pipe replacement was just completed last December. So that's kind of a conclusion of our generally how dams fail, and then just a few different examples there, big and small of incidents. Next, we'll start talking about operation and maintenance of your dam. So we'll take a little break here. If there's any questions.
We don't have any questions yet that have come in on the case studies. There was one that came in right at the beginning when you were still talking about failures. The question is, how many dam failures occur each year?
I don't know the answer to that. I don't even know the answer to that to say in Iowa. As we talked in our last webinar, we have about 4,100 dams, the bulk of those low hazard. Occasionally we're out and we'll see a farm pond that had breached for some reason. Those don't always get reported to us. On our what we call our major dams, we inspect those frequently, so we know when there's events. And so really we had been fairly quiet until these last, it was kind of interesting, last couple of years when Bedford and Waterford opened up. Were really kind of recent examples, but we hadn't seen a lot of problems before that. But like I said, we don't always hear about them either.
And I do have something to add. I've been sitting on this question for about 40 minutes.
Good.
Damsafety.org has an incident database, and it has different incidents that you can search by dates and failure, non-failure, and from all the different states that report the data. So it's limited on what we know about to what's reported. But in the last 5 years, there is 156 entries of different failures from different states. And then 100 of those are from North Carolina and South Carolina from hurricane.
Oh, sure.
So that leaves 56 left.
Yeah, I'm trying to think when the Colorado had their big flood too.
That's right.
Was that 2017 or was that earlier? But
it was earlier.
Maybe that was, yeah, might have been, I forget, but.
Yeah, that was 2013.
Yeah, so, and you know, they are kind of interesting to look at, and just to remind us that these do still occur. You know, we do our best to prevent them. We have a lot better designs than we used to, but we also have a lot of aging dams. So the last two examples for Iowa there, Waterford and Bedford, we're just going to see more and more of. We have a lot of corrugated metal pipes in our dams that really are hitting their lifespans, and so they're going to need to be replaced or lined, hopefully before we get any significant failures.
We have a question on the Johnston Dam.
Mm-hmm.
How did they lower the pool for repairs?
So we really kept a close eye on that, and really, as you saw there, it was kind of interesting. The top of the pipe is what gave way, and so for the base flows, while they were working on a repair plan, we kind of let it just keep going through there, and keeping a close eye on it. For actual construction, I think they kind of pumped it down a little bit. I think construction occurred really late winter, so I don't think there was much of a flow to start with. So they were able to just kind of pump that reservoir down, didn't have a base flow to deal with.
We got another question. How does one repair a dam that has many trees growing on it? And how do you deal with the roots? Are you watching these?
Yeah, I see who submitted that. Thanks, Kelly. That's always a tough one. I don't know if Casey, if you want to talk a little bit about the Plants on Dams manual, technical manual. I know you've more recently looked at that.
Right. There is FEMA has a Plants on Dams manual, which talks about trees and different types of vegetation on the dam and when they do and don't need to go. And they do break it up by sections of where you are at on the dam. If you're at the upstream slope, crest, like the top third of the downstream slope, or at the toe. And it gives some guidance on what sizes of trees can stay or what sizes have to go, and what you should do with the roots and the root balls based on where you're at in the dam.
Do we have that currently linked on our site or not? I forget. I know we added a bunch, but
yeah, I'm not sure.
We'll try to get that one linked, or if you're interested, we can share that link with you. But we do have on the iowodnr.gov/dams page, we do have some links for owners, and if that's not on there now, we'll make sure we get that one on there as well. I'm going to mention another upcoming manual on rodents. They also make one on rodent damage to dams and how to deal with them. So another good one.
We have a new question. What kind of pipe are you using to replace the corrugated metal?
Sure, yeah. On low hazards, we'll still allow CMP to go back, but a lot of owners are starting to switch to different types of plastic. The plastic pipe industry is getting a lot better. A lot of variety of strengths and properties of the plastic pipe is coming along. Instead of corrugated metal, we do usually recommend a smooth metal pipe. It's called. It's a thicker. It's usually a gas pipe, I think, is what it's primarily used for. NRCS uses that very frequently instead of CMP, and it's just a thicker walled metal pipe, and so it has definitely a much longer lifespan and a higher strength than the corrugated metal. So those are the two most common for our smaller dams.
How would tree removal at Delhi affect root migration after removal?
So Delhi, really, the trees made it harder to detect exactly how much water was flowing out of that downstream toe. I don't think they really contributed to the failure, and now they're completely gone. I mean, that entire area, as you saw, was blown away by the breach. And so, like we talked about, if that dam was still there and they were mitigating, taking those trees out and the impact of the roots, we probably would have been okay leaving the roots with because the concrete wall was the main cutoff, but we would have had to look at that. But really the trees themselves didn't necessarily cause the failure or contribute to the failure. They just made it much harder to detect, I guess, the flow that early morning. Or even in the night, they wouldn't be able to look down and see water flowing out before day broke. All right, well, we can talk about another question, I guess, about tree removal. And like we said, I didn't put it in the handout, but we'll get that link to plants and vegetation on dams linked on our website, iowdnr.gov/dams. It really goes through how to mitigate existing trees on embankments. In what areas is it okay just to cut them down to the surface, and what other areas should you try to do more extensive removal? Because it's always a challenge, and that's why we're going to talk a little bit about it. It's a lot easier to keep the trees off initially than when they've been there 20 years and are fully mature. So, but we'll share that guidance, because like I said, it all kind of depends on the dam and the zone of the dam that the trees are in. So I think we'll continue on, and then I think the next section will go a little more quickly, and then we'll take more questions so you can keep submitting them. Appreciate going through those. All right, so in Dams 101, we pointed out that over half our dams are completely privately owned, and about the other half are really local governments. So the state and federal officials really don't take care of that many dams, and responsibility for dams really relies on the dam owner. So it's either, in our case, that falls on whatever land is owned. I guess I rephrase it. Whoever owns the land under the dam is who we first hold responsible, unless there's some kind of easement or agreement in place. So oftentimes a landowner will have given up an easement to build a dam, but the responsibility for the dam has been legally passed to a dam sponsor that is responsible for taking care of that dam. I put a kind of a wordy slide in here on liability. And liability is a tough one. You know, anything dealing with the legal system is a lot of what ifs, right? But common law does hold that storage of water is a hazardous activity. So you are creating a potential hazard. The responsibility for maintaining a dam, like we said, rests with the owner. Safely maintaining your dam and following best practices is probably the best way that you can limit your liability. Doesn't mean that you ever eliminate liability, but if you can show that you were doing everything you could, that might help you if there is a failure in the future. However, that last quote there, as we all know, anybody can sue anybody, and everybody will get sued, basically, if a dam fails. So when a dam failure occurs and there's downstream damages, likely they will sue the owner, they'll sue the operator, they'll sue the engineer, they'll sue any kind of contractors that worked on the dam. Anybody, of course, is fair game. So best practice is to maintain it best you can, to show that you were doing everything you could, but always be prepared that lawsuits can occur if that dam does fail. And so, not on the legal side, but you can kind of think of a dam as an older car. The better you maintain it, the less costly repairs hopefully you'll need in the future. So, you know, you let something go downhill, then its repairs tend to get more expensive than if you're maintaining it along the way. So we'll first talk about the operation side of operation maintenance. Probably should have made these as pop-in bullets, but we'll throw just a bunch of text at you, I guess. So first of all, some of our dams have formal operation maintenance manuals. Some of our larger dams, some of our dams that have gates that have to operate in flood events, those sorts of things. So obviously keep that handy, keep that reviewed, keep that up to date, and then follow the recommendations that are in that manual. The next step is really just keep good records of your dam. If you don't have the original design plans, reach out to us. A lot of times we do if it's a permanent dam. But keep those handy, because if anything happens to the dam, it's handy to have the original plans and calcs for the engineer working on repairs. Keep your inspection reports. Keep documentation of any repairs you've made over the years. And then keep records of seepage and cracks. So if you notice wet areas, see if there's ways to measure that, or the extent of that, and try to track that over time. Same thing with cracks or movement of concrete walls, those sorts of things. Sometimes they don't seem to change year to year, but try to keep record of a measurement at least once a year that says, yep, it's still a 1-inch displacement. It's been that way for 10 years, or you could say, you know, it seems to be moving about a 1/4 inch a year. So just part of that record keeping. Periodic inspection, we'll talk about more. Obviously, very important just to see what's going on. And if your dam has an emergency action plan, you certainly want to keep that updated, and also see if there's any downstream development that impacts that plan. We talked about emergency action plans in the last webinar as well that you could watch if you haven't. And then anytime you have anything that's sort of movable on the dam, it's good to move those items at least annually. So if you have a drain gate that can be open and closed, try to crank that a little bit every year. You don't have to fully open it, but just get everything moving, make sure it works. And then obviously do, you know, anything with moving parts requires maintenance, so make sure that's properly greased, and if it needs repairs, get those repairs scheduled and budgeted so they can be fixed. Other things with watching the dam are just watch your pool elevation, see if you have any changes. Keeping floating debris out away from the dam. If you have instrumentation systems, I guess, you know, hopefully that's in an O&M plan. You know what those are there for, and know what to watch and how to measure those. And then if you have any kind of alarm or warning systems, make sure those are being monitored. So inspections, and I tried to put some general guidelines on here, but really it does depend kind of dam to dam. If you have a low hazard dam, it's good to, you know, at least have a casual look at your dam at least weekly, just to say, yep, everything looks okay. You know, if you never look at it, you're not going to detect if there's new issues arising. Our high hazard dams with a permanent pool behind them, really, there should be some general eyes on those almost daily, just to make sure nothing unusual is happening. And then you'd probably want at least a weekly full walkthrough, you know, along the embankment or along the toe of that high hazard dam, just to make sure nothing unusual is occurring. Other smaller, you know, our smaller farm ponds and those sorts of things, you could probably do a walkthrough every month or so, just to make sure nothing unusual is happening. But anytime we have a large rainfall event, you know, that's when we're testing those two primary criteria for a dam is how well they're holding water and how well they're passing large flows. So when we get those, you definitely want to make a visit to your dam. And then that goes along with the next bullet, which is first filling. You know, we don't know. We've learned a lot of lessons over the years, and we do a really good job designing dams now. But you know, you never really know until you put water behind it. So dams need to be watched very carefully during their first filling, and that can go for first filling of their record high levels too. So you might have a dam that fills up and it's a normal pool, and it can be a matter of years before we get a large enough storm event that we see a 5-foot rise or a 10-foot rise of that pool. That even though it's designed to handle that, once again, we're hitting a new level that hasn't been tested. We need to keep a really close eye on that dam, make sure we're not discovering any new weaknesses, kind of like Lake Delhi. You know, the first time we had that much water, we found that weakness and it failed. So obviously, we're looking for early warning signs, right? We're trying to catch any problems before they progress. So if we can catch a seep that's starting to have a little bit of a cloudy discharge, and we can lower the water level, or we can add some filters, or we can try to cut that off through different grouting or techniques, we can prevent that cloudy seep from getting worse and going to a full piping failure. Then of course also, you know, we're looking for, you know, O&M needs. So sometimes things can be expensive, a new pipe, major work, new riprap. And so we need to take a look at our dam and say, you know, the next couple of years, I'm going to have to set aside some money or put that into our budget, homeowners association or city budget or personal budget to try to get this work done. So the sooner you can identify needs that are before they've gotten so bad that it's going to cause a lot of cost, the better you can get those budgeted. And then of course also, like we talked about, with if you have any instrumentation that needs to be checked, you're doing that during your inspection. So what are we looking for when we do an inspection? You know, general stability. Do we see anything? Do we see any movement? We don't like movement in dams. We don't like movement of the embankment, movement of the soils. Like we talked about, a common problem with concrete walls or spillway chute walls is that they can move over time due to frost heave or just age or cracking. And so we're trying to track that movement. And then obviously erosion. We have a earth embankment dam. Water is always trying to wear that down, so we're trying to watch for issues of erosion. It can especially occur at the groins where we have that focused flow between the dam and the abutment. Alongside spillway walls, we can get erosion. At our spillway outlets, we can get erosion. And then, yeah, looking for wet spots. It's really important to walk that toe of the dam to see if we have any new wet areas. And if we have wet areas, you know, what's causing it, and what do we know about where that water is coming from? How well is our grass cover doing? Do we need to clear it? Do we have any, groundhogs or muskrats or beavers issues going on? And we talked about concrete surfaces. I pointed this out last time, and I don't want to spend a ton of time in this webinar because I just want to point you to this free, very detailed, well done webinar on inspecting dams. It really walks you through all the things that you should be doing, looking for, how to conduct them, what kind of equipment, parts of a dam again. So that link is here, and it's also in the handout. So as we talked about last time, I would encourage you to, if you're taking the time to watch me go on about this stuff, Paul Swigert is a national dam expert, dam engineer as well, and does a great job with that webinar. So I'd encourage you to watch that one when you have some time. So now we get on the maintenance side of the O&M. This, unfortunately, is kind of a something we see way too frequently. It's kind of labeled here as a midlife crisis. So, we have a nice new dam, it's got a great grass cover, new pipe, everything's working well, and then it's kind of neglected for 10 years. And then we start to see trees overgrowing the dam, and we're seeing unchecked rodents and groundhogs and things burrowing in. Over time, those trees can fall. Or another problem is sometimes we tell owners, you should really cut your trees, and so they go and they cut their trees and then they just leave them there, which doesn't really solve the problem of being able to mow the dam and being able to easily inspect the dam when you're trying to walk over all these trees and brush that have been cut, but now they're just piled up on the dam. So it sort of has stopped the problem, but still hasn't completely fixed it. So try to go to that extra effort of getting the trees and brush off and getting reseeded, which, I say that and it sounds easy, or we make it sound easy, but I know it's a big effort. And so usually we do say if you do have an overgrown dam, step one, get in there and see how much of the underbrush can you clear by hand, getting some smaller equipment, brush hogs, those sorts of things to kind of clear that out. Can you get, before maybe you have the money or the means to get the large trees off, can we get at least the underbrush cleared and some grass down so you can at least walk the dam, you can inspect it, we can see if there's problems, we can see if there's erosion. So that's kind of step one, and then clear trees as you have budget or the means. So it's definitely a phased project. We know that a lot of times you don't have just a dozer at your disposal to go and start pushing trees over and get that clear, and it takes time to get that grass established as well. So nothing is really easy about it, and so that's why we do try to get on owners to mow or burn your dam. Sometimes we do native grasses or native mixes. So do try to burn that every couple of years, or at least mow it once a year with a tractor or something, so that you can keep that heavy trees and brush down. Because once they get going, it's just that much harder to clear. So as far as the embankment goes, talked about getting good stand of grass or native grasses. Keeping your outlet works clear. You can get, like we said, you can get erosion, scoured areas need to be fixed. Waves can get going. Oops, there's a misspelling, sorry about that. Upstream. And then our rodents that can cause a long-term damage. I guess I'm kind of beating this hard. We talked about these. There's just a picture of mowing. Obviously, we have too many of these that are still out there. That it's pretty easy, especially if we get ownership changes or things like that, or the tree just the dam just gets let go, and it doesn't take long for those trees to get going. A couple examples of just erosion. We can get really focused. Ruts in our embankments, especially here, is kind of in that groin area where water flows, and then we just get a channel going and it just gets worse and worse. Here's some runoff from a roadway carrying erosion, so we want to get those repaired. Usually our dams either have a bench that they'll design that kind of breaks up the waves and prevents some of this heavy cutting, or oftentimes we'll have small riprap or large riprap along the upstream shore, because waves can really do long-term damage. You know, you just think day to day that wind pushing that water, it doesn't take long to start cutting away. So a couple examples here of that. And then of course, yeah, we have pretty robust groundhog population in Iowa that love to dig holes. You also get muskrats on the upstream side. You know, isolated, they're not that bad. You get more and more, and it just gets worse. You know, kind of the worst case scenario is if you get a burrow on the downstream side and a burrow on the upstream side, and they start to join. Basically, now you've got a pipe. Or even if you have a burrow on one side, you've just shortened that piping path that much shorter. So another thing that's, you know, easier said than done sometimes is getting that under control, but you want to do your best. And like I said, there is also a technical manual put out that kind of talks about the different types of animals that can impact your dam, and some different ways to repair the damage and ways to deter them are available in this manual. Like I said, in Iowa primarily, you know, beavers will occasionally build berms upstream of our intakes, and also maybe downstream of our outlet works too, backing water up on our thing. But they generally don't damage the dam itself too much. But then groundhogs and muskrats like to burrow in. So spillways. Obviously, the whole point of having a spillway is to pass the water, and so if we have debris blocking those, that's going to impact our capacity, which would lend to higher risk of the dam overtopping. We want to make sure our gates, if we have them, that they work, that we can open and close them. You know, any metal can rust or deteriorate, so you know, budgeting, planning on sealing that, painting that, repairing those. And then as we have grouts or as we have joints and cracks opening up, we need to reseal those. So when we have concrete chutes, those joints, you know, really after 10 years, a lot of that joint sealant gets popped out through ice and things. And so that's kind of also a major maintenance thing that needs to be done, is to reseal the joints of our concrete chutes so they don't get water flowing underneath them. And then concrete itself, concrete quality can vary quite a bit. It's interesting. Sometimes we can go out to a dam that has 100-year-old concrete and it looks great. Another dam has 10-year-old concrete and it's spalling and in bad shape. So all depends on the original quality and construction methods that were available when they built it. And so that can be costly. So that's one of those things that you want to note and start to budget if you have large areas that are starting to spall, to get that resurfaced. There is also, if you suspect flow underneath your concrete chutes, I've seen ground penetrating radar used occasionally, which could, you know, it's not super accurate, but you can tell if there's definitely voids under there or not, and if they're changing over time. The other way that's commonly done is that they actually drill cores. So they drill a small hole in the chute floor and just measure down. If you hit your subbed that's supposed to be there, you're in good shape. If your tape just kind of keeps going into the void, you've got problems. And then you have to develop a plan of either grouting that, or if it's so extensive, is there just something fundamentally wrong with the chute and it needs to be replaced. So obviously we can get a lot of debris build up quickly. And example of a gate that should be, you know, maybe this gate's never planned to be used. It's really just to draw down the dam for emergencies or for maintenance. And so that's kind of our struggle, is that a lot of times there's just a fear that they don't want to open them. They might get stuck open, which is a legitimate concern. But if they are properly operated and maintained, then they should be able to be safely opened an inch and closed. But obviously, the longer they sit there stuck, the less likely anyone's willing to ever touch them until they need them. And then we don't know if they do work when we do have an emergency. Just an example there of some poor concrete that needs to be repaired. That's some of that spalling we talked about. And this, we talked a little bit earlier about corrugated metal pipes. This was one example we had a few years back that the design flows and everything worked out that they could put this smaller plastic pipe inside the older corrugated metal pipe that was starting to rust through. So one way that's sometimes possible and cost effective is to slide a new pipe inside the old metal pipe, and then they actually grout this, replace cement grout between the two to kind of seal everything up. So that's one rehabilitation method, and the other one, as we talked about, is just full digging out the old pipe and putting back in a new one. So each dam's a little different on which method is more feasible or more cost effective. And then a few other things are looking at the outlet channel itself. We can have erosion that progresses where the water comes out. So flipping back to this picture, this would be the outlet channel. In this case, it's pretty stable, but occasionally we get, after large storms and things, that can get pretty turbulent and start to erode. Any warning signs you have around the dam should be checked and replaced. Looking at your instrumentation monitoring systems, maintaining those, and then, we've talked about the upstream slope protection. Even if it is rock, a lot of times, riprap quality can vary quite a bit throughout the state, depending on what was spec'd or what was delivered. Sometimes, what was 1 foot diameter rock riprap, after a few years becomes 3-inch stone and starts to wash away. So sometimes you'll need to replace even upstream rock protection. And I wanted to touch just a little bit on public safety at dams. So it's a little bit different. It's not something that we have as firm in our rules or requirements, but it's something as a dam owner, you're still open up for liability for people getting hurt at your dam. So the first step is to, anytime you can control public access, try to do that, putting up warning signs, adding fencing, those sorts of things. Couple examples here. This is the new constructed Lake Delhi, but they've got fences up along their walls so someone can't fall in. They've added buoys upstream of the dam to help prevent any kind of boats or swimmers, those sorts of things, to know that that's a dangerous area and to stay out. And some signage that says no trespassing private property, those sorts of things, to try to minimize protecting people kind of from themselves of getting into dangerous situations on your structures. And then as far as people using the river or stream, I wanted to point out that the DNR does have a sign manual for, these are really set up for like low head dams on our rivers, of best practices of how to properly place warning signs for people on the river around those dams. But any dam can provide really an attractive nuisance for people to jump off your spillways or ride down your spillways or jump off your structures or swim near it. So there's a lot of guidelines out there as well on public safety at dams. So doing good on time. That's kind of what we were going to talk about for today's webinar. As we talked, talked about how dams fail and that they do fail. We have incidents every year, so it's important that we do due diligence and keep on top of our O&M to help find any kind of indicators that failure is on the way, and also to prevent failure by keeping our dams well maintained. And there's a lot of resources out there. Like I said, we just hinted at a few. There's a few links here that are in the slides, and these are also in our handout. A good place to start is damowner.org. That has a lot of good resources. We link to some of them, but I think there's a lot more, and that web page is by the Association of Dam Safety Officials, and they're always adding new content. And they're working on a series of videos as well. They have a nice Dams 101 video on there, and there's more coming. And then, as we talked about last time, which is maybe more relevant to this webinar, is damfailures.org. is a really nice website that's split into, there's two ways to look at it. You could look at case studies of different dam failures that have occurred, and they have a lot of them. And then they have lessons learned. So they have all the things that you could go to the lessons learned and say, well, why do I need to keep trees off? Or why do I need proper design, or those sorts of things. So there's a lot of different specific topics you can read more about and get smart about dam safety. And then we talked about last time, we don't spend quite as much time on our low head dams, a little bit different beasts. But we do have a nice page on our DNR website about mitigation and efforts going on for low head dams around the state. And if you're a dam owner that has questions about fish and plants in your ponds, our fisheries biologists have put together a nice page about those things on our Iowa ponds and their fishing section of the DNR website. So I encourage you to check that out. And you can also contact them and ask them for advice or how to stock. So we'll do another kind of a final question break here.
We've got two questions currently. The first one is regarding inspections. What sort of things would you look at with a low head dam on a periodic basis?
Okay. Yeah, it's interesting. A lot of our low head dams around the state, we inspected on a yearly basis up until about 1990. From the 50s to the 90s, it was a rule that said every mill dam, every low head dam would be inspected yearly. And those inspection reports basically consisted of, yep, it's still there, looks the same. Took a picture of it. Because it's really, those are tough to do cursory inspections of, right? I say that in that you can certainly look at those and say, hey, it's there, it looks solid. But really that's a case of hiring a specialist where you need a good concrete firm, or you might even need a diving firm to periodically go and probe at the downstream toe of that and see is there undermining occurring, is there scour occurring below the water that we don't know about. In most cases, you can't just dewater those, right? They're on a river, we have constant flow. So really those are special inspections. And unfortunately, we don't really have a good list of people that do that. So we always kind of point people at local engineering firms, reaching out to them. If anybody knows specialists in that, let us know. We could share that. But so I mean, really, you're doing a concrete structural analysis of those, and you have to kind of look back and say, well, they're all built a little different too. A lot of them are solid concrete, but some of them started out as a rock crib dam, meaning that it was just timbers, kind of a wood frame filled with stone, and then later on they overlaid it with concrete. So those are much more vulnerable to cracking and damage. So as an owner, I guess, yeah, I would periodically 5 to 10 year basis probably get you know, a firm that specializes in concrete structures to do a detailed report for you and say, you know, has this dam stable? Is it showing any signs of wear? Potentially have a diver go down and see if there's any kind of scour or undermining. But other than that, it's pretty tough, even for us to go out and tell you if there's something wrong with it. I mean, we can pretty much go out and look at this and see the same things you can as an owner and say, well, it's still there. You know, maybe there's some cracks, maybe there's not. You know, the cracks gotten worse. We don't know. It's just really hard to do that. So those do take some specialty and some cost to do that.
The next question is on maintenance and trees. Can you spray the trees for removal?
Yeah, I mean, if they're smaller, you could certainly spray them. At some point, they have to be removed, really. I mean, ideally, like we said, ideally you want to mow your dam at least once a year so that you can keep the woody brush down as well. So if you spray it to kill it, at some point, you know, you do want to remove it. You know, a lot of times you can cut a smaller tree and maybe you spray the stump with some Roundup or another product, and that'll stop it from resprouting. So that's useful in spraying the stumps or treating the stumps so they don't resprout. But
another question, can you comment more on dam owner responsibility when downstream gets urban development later and the need for upgrades liability?
Yeah, really what we try to do when we permit new dams is look at the potential for development. And so if we do try to look ahead to point out to an owner to say, well, you know, we're going to make you design this assuming there will be development downstream, but that doesn't always happen. So sometimes you can get development downstream of your dam in your breach zone. And so when that does happen, the dam will be required to be upgraded to meet the more stringent criteria. The way I always look at it, and different states do it differently. Some states have passed laws that do share that responsibility for the upgrades, but I always think of it as, you know, by you building something on your property upstream, you don't get to take away the value or the rights of people downstream that want to utilize their land for development or whatnot. That's, you know, outside the normal 100-year floodplain, but now has become a breach zone because of your dam. So we put the burden on the dam owner to, we try to catch those developments when we can. There are some rules about building downstream of a dam, and if we can keep people out of the breach zone, we do. But when it does occur, generally the dam owner is responsible for making those upgrades to meet that higher hazard criteria. I think that's caught up. Like I said, you guys can always follow up with us with further questions. And I'll just leave it with that we do have 2 more of these coming up. I thought this was a good idea to do all 4 of these in 1 month. So anyway, all right, so now tomorrow I'll start working on slides for next week. But we do have 2 more coming up. Next Wednesday, same time, we're going to talk about, you know, how do you get a hold of an engineer? Who are these engineers, and how do you find them, and what are some typical costs, and those sorts of things. So we're going to potentially have some area engineers maybe help us out too in answering questions, but still kind of planning that one out. But we're going to have some general help for. That's one of the questions we get. It's like, well, what do you mean I have to hire an engineer, and how do I find them, and what's it going to cost? So we're going to go through some of that because obviously there are times when it's gone beyond normal operation maintenance, and now you do need significant repairs, and those repairs should be designed by an engineer. So there'll be times when you do need to hire an engineer if you don't have one in your city or county or staff. And then our final week, is our kind of our most technical, and that's where we're going into, the dam design process, and the best practices and the different tools and things out there and what we expect to see when we review them for permits. And then going over some of the potential changes that we've drafted up for our rules. You'll be hearing more of Casey on that one, so that'll be a little change, right? Casey's
That's
excited.
right. That'll be a nice fun change.
All right.
We do have maybe one last question.
Yeah.
Is the PDF of last week's presentation going to be available? And this one?
Yeah, I guess on our website we shared the video, but those handouts are gone, I guess. So we'll when I get this video posted, I'll go ahead and put the handout and the slides linked along with those. So if you go to that our dam safety webpage, it'll have registration for the upcoming two, have the videos of last week and this week, and then below the videos I'll try to put links to the handouts, because I know if you don't, I encourage you to download them now, because like I said, once the webinar is over, there's not a way to click those. So we'll get those linked on the website. Thanks, Brad, for the reminder. All right. Well, that brings us, this one I went the full 2 hours. I don't know if next week will be 2 hours or 1 hour, but we kind of go through them as we do. I appreciate once again, all of you for joining us and taking the time to learn about dam safety and take care of your dams. And that's really all I've got. So we look forward to seeing you upcoming webinars, or reach out to us if you have specific questions. Thank you.